Good morning, everyone. Can you hear me? Okay. Welcome to this new doctoral meeting, the first one of the year 2025. I'm going to start with a little presentation of our speaker. That is Álvaro Goldar. He obtained a bachelor in computing engineering and master in high performance computing in 2021 and 22, respectively. He is currently doing his PhD, doing sensitive image processing, such as multi and spectral images, which can be captured by satellites and UAVs. His presentation is named Deep Learning Techniques for Accurate and Efficient Biodiversity Monitoring with Limited Data. You have 20 minutes to do the presentation, then after you have a small time to do questions. Yeah. So you can start.
Okay. So hello everyone. Thank you, Mario, for the introduction. And thank you everyone for attending this doctoral meeting. So let's get started with a quick overview of what we will cover in this presentation. First, I will provide some context and describe the specific goals of my PhD. After that, I will present two works we have published as part of the PhD, and I will conclude the presentation by highlighting our main takeaways and discussing what we are working on. So for a long time, the human population has been transforming large areas of land for different needs. For example, to build infrastructure such as cities, or to exploit natural resources through activities like agriculture or forestry. However, many organizations, such as the United Nations, are now putting attention on the need for sustainable development goals to protect the health of our ecosystems. And this is because all these land transformations are driving quick changes in our ecosystems, often without fully understanding the long-term ecological consequences. And a clear example of this can be found in Galicia with the eucalyptus tree. For a long time, eucalyptus plantations were promoted for their high production, but the eucalyptus is also much more flammable than native species. So over time, this has increased the risk of wildfires. So nowadays, local authorities are working on plans to reduce the presence of eucalyptus over the following years. And because of this, it is now becoming more important to monitor the biodiversity of ecosystems. And to monitor the vegetation of an ecosystem, we can use remote sensing technology. Here we have drones and satellites that capture images of large areas of land. And these devices typically carry advanced sensors that capture detailed spectral information across many bands. So as we can see in this figure, these remote sensing images typically have more than the usual RGB bands, and this allows a detailed analysis of the different elements that are in the area. On another hand, we have deep learning, which has revolutionized the analysis of data in many fields, including remote sensing. However, to monitor biodiversity, we have one issue, and the issue is that each ecosystem has its own plant species. So these studies usually work with small data sets that are made for specific areas. And we have to face the following challenges. We have limited label data, because manual field surveys are time-consuming and expensive. We also have data imbalance, because some vegetation species are more common than others in ecosystems. And despite the detailed spectral information, different vegetation species share similar spectral profiles. So to help address these challenges, this PhD focuses on the development of deep learning solutions that try to make the most out of the available data. More specifically, we will be taking existing works on monitoring biodiversity that either use traditional machine learning or basic deep learning techniques, and we will try to improve the prediction accuracies. And ultimately, our goal is to provide insights for other researchers on how to design accurate and efficient solutions to monitor the vegetation of ecosystems. So with all of this in mind, I can now introduce the first work, which is RESBA-GAN, a residual balancing GAN with data augmentation. In this first study, the goal was to classify elements near Galician rivers, to distinguish native vegetation from potential threats. So for example, in these images, the red area corresponds to part of a river, and we can see below the river a series of native trees. However, in the same image, we can also see an invasive species, more specifically the eucalyptus, and we can also see a road below the river, which is an artificial structure. In total, this study involved the analysis of 8 river sites, and for each river site, we had a large high-resolution image that captured spectral information across 5 bands. And the 8 datasets present the challenges for deep learning that I was describing earlier. First, we have limited training data with as few as 4,000 samples in some datasets. We also have strong imbalances among different classes. So, for example, on the Iras Dam dataset, we have 100 samples for pines, and at the same time, we have over 2,000 samples for the native trees. And lastly, despite having information across 5 spectral bands, we can see similar spectral signatures for all the vegetation classes. We can compare this with the non-vegetation classes, which are much easier to differentiate. Luckily, in this case, we will be able to use the high resolution of the images to address these challenges. And this is really interesting because despite the similar spectral signatures, different vegetation species have different textures. So, for example, we can see on the right side one species of trees and another different species on the left side. So, if we take groups of pixels for the classification as shown in this figure, we combine the spectral information of the image with the spatial information of tree textures to help the classifier improve the classification accuracies. And this is a diagram of the solution we have proposed for this problem. In essence, we have on this part the input samples of the dataset, and these samples are processed by 2 different modules that I will explain later. We have an autoencoder module and a GAN module. And inside these modules, we have our final classifier, which is a ResNet-based network, and it corresponds to this D component. And in summary, this classifier is integrated into a data augmentation framework to help improve the classification accuracies. On the one hand, we are using traditional data augmentation by applying geometric transformations to the original training samples. This includes, for example, rotations or flips. And we are also using a generative adversarial network to generate new synthetic data. For context, a GAN network usually consists of 2 components. We have our usual classifier, and we have a new generator network that produces synthetic samples during training, and these samples are fed into the classifier along with the original data. So these new variations help the classifier improve the understanding of the different classes. In any case, it's important to note that our initial experiments with GANs were not successful, and this is because these architectures are really hard to train when facing imbalanced datasets. So as can be seen in this image, the original generator was only able to create samples that looked like vegetation. So to address this problem, we explored the existing research on how to try to use GANs for these types of contexts, and we found out the balancing GAN to be a promising solution. The balancing GAN is a modification of the original GAN architecture that introduces multiple changes to allow the generator to work properly with imbalanced datasets. So as can be seen here, it is now able to produce realistic samples for all the classes in the datasets. More specifically, BAGAN proposes multiple modifications to the GAN architecture, and we are using 2 of those modifications in our solution. First, we have an autoencoder initialization, and this means that we train an autoencoder architecture before the original GAN architectures. Once the autoencoder is trained, we transfer the weights to the GAN networks instead of using random values as initialization, which is the usual approach, and this helps a lot in stabilizing the training with small and imbalanced datasets. Additionally, BAGAN proposes simplifying the usual 2 outputs of the classifier into a single output. So we have also incorporated this modification in our proposal. And ultimately, all of these components allow the ResBAGAN classifier to improve the classification accuracies over the original work, which is using a series of traditional machine learning techniques. In any case, it's important to note that all these data augmentation techniques introduce a certain overhead during training. In any case, the final speed of the classifier isn't affected. And this concludes our discussion on ResVagan, and we can continue with our second work, ResNetS. In this case, the goal of the study was to create biodiversity maps, vegetation biodiversity maps, for German grasslands. And these maps display different properties about the number of vegetation species that can be found in different areas. So, for example, on this image here, lighter areas indicate that there are more vegetation species, while darker areas indicate that there are fewer vegetation species. And ultimately, the goal was to help understand how the usage of different lands affected the biodiversity over time. So to this end, the dataset contained information measured across 4 years, and for each year, a satellite visited each grassland plot 16 times, capturing spectral information across 10 bands. So our input data, in this case, looks like time series, and like in ResVagan, we are facing a limited data context with only 400 training samples. However, in this case, we are combining the spectral information of the dataset with temporal information. And this is really interesting because different vegetation species start to bloom at different times during the year. So in some way, the time series encode the growth patterns of the different vegetation species, helping understand how many species are found inside each plot. So the original work of this study proposes the usage of a multi-layer perceptron for the analysis of this time series data, and this is a really simple deep learning architecture, and many more advanced alternatives are available, such as recurrent neural networks, transformers, or even convolutional networks that are made specifically for time series data. So initially, we decided to evaluate existing models to see how they could improve upon the original solution, and we found out inception time to perform the best. More specifically, inception time is a convolutional network that is adapted from the inception family of image processing networks. And as can be seen in this representation, inception time processes the input data by applying a series of parallel convolutions to the information. In any case, we noticed that most of the convolutional networks that are proposed for time series analysis are usually based on previous advances on image processing networks. And in image processing, modern convolutional networks are usually based on the ResNet family of networks, which uses a sequential design, as shown below. So we had the following idea. What if we take ResNet, we adapt the model to our time series data, because on the one hand, the resulting model might be able to outperform inception time, but additionally, this will allow us to integrate innovations from the latest ResNet models that are used in image processing to boost the prediction accuracies even more. So this is where ResNetS, the proposed solution, comes from. We can see this model as our initial adaptation of ResNet for our time series data. And we started by replacing two-dimensional convolutions with one-dimensional convolutions, and we applied multiple architectural changes to optimize the performance of the model with sequential data. Additionally, we are using a series of model-independent techniques to improve the accuracy of the model even more, such as advanced training techniques like checkpointing or warm-up phases, and we are also using model ensembling to combine the predictions of multiple individual models into a single one for improved stability. And ultimately, the proposed model is able to achieve a comparable accuracy to the inception time model with a much smaller architecture. More specifically, we can see a slight prediction accuracy increase, but with a much higher computational efficiency, achieving almost a 70% of speed up. So in summary, we can see how deep learning offers powerful solutions to develop different techniques to monitor the vegetation of ecosystems, but we have to face challenges like limited label data, data imbalance, and similar spectral profiles across different vegetation species. And to help address these challenges, this PhD focuses on the development of deep learning solutions that try to maximize the extraction of knowledge from the available data. And this is done by using the multiple dimensions of remote sensing data and by using a series of advanced deep learning techniques. Moving forward, our intention is to continue working on this last problem because, as I was mentioning, we believe there is potential to continue improving the ResNet's architecture by incorporating innovations from recent ResNet models used in image processing. And now we also have access to the full satellite image time series data that was used to create the dataset. And this is really interesting because the time series that we analyzed represent the spectral information of a single pixel in each plot. But we now have access to the full information for all the pixels in all the plots. And this allows to complement in a single model the spectral, temporal, and spatial information to boost the prediction accuracies even more. And that concludes the presentation. Thank you for your attention, and I'm open to any questions you might have.
Thank you, Álvaro, for your nice presentation. Now it's working. Do we have any questions? Yes.
Hola. Thank you, Álvaro, for the presentation. A little question, from which satellite are the images of the second work?
These images are from the Sentinel-2 satellite, which is part of the European space program.
With all the bands? Or
No, I believe the Sentinel-2 has 12 or 13 bands, but we are using just 10 of them.
Okay, thank you.
Yes.
Thank you, Álvaro. Well, a little question only. In the first part of your work, with the classification of this kind of different kind of objects, I mean, you use the patch, that the patches are obtained before with another. Yes.
Yes, those patches.
Those patches.
Yeah.
Yes. The size of the patch influence in the results. I assume that the size of the patches influence in the computational cost.
Indeed.
But in the quality.
Yes, the size of the patches impacts the final quality because, in theory, larger patches provide more information for the classifier. In any case, it's important to adjust the patch size to the size of the elements that are captured in the scene. Because, for example, here the size is tuned to ensure that each patch contains mainly pixels of a single class. Because if we make the patches too large, we might combine pixels from different classes, and this will hurt the final performance accuracy.
Okay. Okay. Thank you.
Thank you for your question.
Thank you. It's not. I'm not sure if it's working. Yeah. It's not very adequate that I make a question because I'm the PhD supervisor, but it's only to ask you to explain more about the second work, because the first work is based on determining classification, and in the second one you are determining the values of different biodiversity indexes.
Yes.
So it could be interesting to give more explanations on the second part, because I think that it's interesting. The
And what's
determination.
the final goal of the study?
Yeah, of the second one.
Okay.
Thank you.
So in the second study, we are predicting 3 different biodiversity indexes. The first index measures how many species are found in each area. For example, this corresponds to this figure that I'm showing here. And we are also predicting two additional indexes that indicate the balance of the different vegetation species to try to understand if we can find in an area many samples of a single vegetation species or if it is more evenly distributed among the different vegetation species. I don't know if you would like to some more explanation or.
Yeah, it's fine because I was thinking now that in this figure, for example, it's not very clear that there are not different, there are not single species, but mixtures of species. Yes. These indexes.
Yeah, I don't know if you can see it well with all this light background, but this image corresponds to a plot that, for example, has a low number of vegetation species. I believe there is one or two vegetation species. But for example, here you can see the grass as well as a series of flowers. For example, we have one color over here, yellow flowers over here, white flowers over here. So all the plots look like this. We have different vegetation species in the end.
And finally, another remark that is interesting, now that you have a few minutes more, is that is the result of a collaboration. It's not easy to make a collaboration with different areas. It's an interdisciplinary work, and it's interesting to enhance this. I don't know the difficulties of the collaboration. You can explain more if you want.
Yes, I hoped that the numbers of the authors will be here, but it is compressed. This was part of a collaboration with a series of German researchers. In fact, as I was mentioning, our first work was made on Galician rivers, but this second work is for German grasslands. And it was an interesting experience collaborating, let's say, online with people that you have never met in face-to-face. But it was a rich experience because in the end we are mainly concerned with the technical part of the study, with developing the deep learning architecture that allows the analysis. However, this other part of the group is more focused on the ecological consequences of the study. So the final result is pretty interesting to read because you can clearly compare my first work for the PhD, which is, you can see all the text, and the text is focused on the technical aspects, but the second one has a more strong emphasis on the actual impact on the society. So a really interesting experience. And I believe if everything goes well, the last work that I intend to do as part of the PhD will be also in collaboration with this group of researchers from Germany. So let's see how it goes.
Do we have more questions? I have one.
Okay.
Okay, it's regarding the first work.
Okay.
I think it's in the slide 18. That one.
Okay.
My question is, when you use the autoencoder to generate the new samples, do you do this in an end-to-end model, or is first you use the autoencoder and then you train the GAN model, or is or something like?
In separate phases. First, we train the autoencoder, and once the autoencoder is fully trained, we transfer the weights to the GAN networks. So we have like a two-step training process. Thank you for the question.
I think this is not working.
My question is, what was your experience, or what is your experience in this way? When you review the literature and want to compare your methods with other works in this topic, did you find easy to obtain the models, the architectures, the results, or you feel easy to
That's a really good question. My personal experience is that reproducibility is quite challenging because I believe we are making progress nowadays, but compared to a few years ago when I started in this research area. But my experience is that most works don't publish their code, nor the trained models, nor the data sets, so you can't reproduce anything, and that can be pretty frustrating. Additionally, many times that I tried reproducing other architectures, you can find one specific description on the text of the paper, but if you look at the code, the actual network is doing something else. So this can be pretty frustrating, but I believe that we are making progress because nowadays I feel that a more large percentage of works are trying to provide all the data for other people for reproducibility, which is a crucial pillar of experimentation.
And in this way, do you think that the researchers from other areas like the ecological or something similar feels this necessity of this open access to the code?
If I understood right the question, it is if, for example, the ecological researchers are more likely to provide materials for reproducibility.
Used to analyze the data from, out of the computer science or computer engineering researchers, other researchers, do you think that are worried about this?
Well, my experience is somewhat limited because this is the first time that I really interacted with researchers outside of computer science, so I couldn't really tell if they are more likely to provide materials for that reproducibility. Thank you for the questions.
More questions? No? Thank you again, Álvaro, for your nice presentation.
Thank you for your attention.